RM10 unmanned aerial vehicle as an autonomous aerial sensor system. So here's the conceptual overview of the system, and it's subdivided into three parts: the UAV, unmanned aerial vehicle, the aircraft, a ground control station on a PC, and a safety pilot, which is required by law. So if we take a look at the UAV software component, you can see the attitude heading reference system, functional unit 1, produces orientation or measures the orientation using the IMU. GPS gives the location of the aircraft. An inertial navigation system takes the orientation information from the attitude system and the location information from the GPS. And then it also estimates airspeed using a pitot tube with a dynamic pressure sensor and a barometer it uses to estimate the altitude. And then based on the information it gets, it determines what trajectory to take up next to reach the next waypoint. This is passed on to the main guidance control, which basically manages the flight modes and just oversees the operation of the entire UAV. It's basically the main function of the microcontroller. And then functional unit 5 houses all the PID controllers, the control systems, to basically fly the aircraft and stabilize the aircraft. And that's passed on to the functional unit 6, which is the servo control, which basically generates pulse width modulated signals to send out to the servos and thus control the control surfaces on the aircraft. And then also functional unit 7, the telemetry. The main guidance control basically decides what to send out through the telemetry over the radio to the computer, the ground control station, and all those messages are facilitated by the telemetry component. There's also functional unit 8, an interrupt handler, that basically just processes UART messages from the GPS and the telemetry radio, and it also has interrupts to measure the pulse width signals on the RC receiver, so that you can have manual control over the UAV, and also a switch on the transmitter enables or disables the autopilot select. And then moving on to functional unit 9 is the fire detection. So it uses the air composition sensors and neural network, and then basically determines whether or not there's a fire and passes it on to the main guidance control. Okay, so the attitude heading reference system takes the IMU sensor readings from the accelerometer and the gyroscope and the magnetometer, and then it has to do an IMU position offset compensation. This is because the IMU is not mounted at the center of gravity, so in order to measure what's happening at the center of gravity, you have to do a transform for the position. So then after performing the offset transformation, you need to use the centripetal acceleration, which is calculated from the angular rates from the gyroscopes, as well as the speed of the aircraft. So then once you have the centripetal acceleration, you can minus it from the measured acceleration to get the true gravity vector. And then you can calculate the pitch and the roll angle. So then the problem with the gyroscope is mainly the gyroscopic drift, which you can see here. And then in order to get rid of that, I designed a complementary filter using the angular rates from the gyro, which are integrated, and then you get an estimated angle, and then also using the true gravity vector, you estimate the angle from that. So then you use a high-pass filter to filter out the gyroscopic drift, which is a constant bias, and then to filter out the accelerometer noise from the motor and general flight, you use a low-pass filter, and you combine the two to get an estimated angle. The Laplace domain form of the previous diagram just becomes this. Theta A is the measured angle from the accelerometer, and omega is the angular rate from the gyro. 1/s is the integration, and tau is a time constant for the filter. So then using alpha defined as a function of the time constant and the sampling time, we simplify the previous equation to get the pitch and the roll rates in discrete time based on z transform backward difference. So then I took some readings and looked at the fast Fourier transform and determined where the noise was sitting and where the bias was sitting. You can see that in the report. And then the alpha value that I calculated was 0.985, and I took some readings and rotated it through the axis. And then you can see here the blue line is the filtered pitch, and you can see that towards the right when the IMU is placed flat, the gyro starts to deviate from the rest of the information, and that's due to gyroscopic drift. But you can see the blue filtered pitch hugs the accelerometer, the red value, and so gyro drift is completely eliminated. So then the magnetometer is used to measure the heading of the aircraft. I decided to take the route of using the magnetometer because integrating the gyro wasn't such a great idea because of the gyro drift, and then the accelerometer doesn't help, so you can't use a complementary filter because you don't have any other reference. So I decided to use the magnetometer, but it also had a few problems. The first of which was hard iron effects, which you can see by the offset. The blue values in the plot are offset. The center is offset from the origin because of the hard iron effects, which are due to things like the battery and all active components. And then the reason why it's ellipsoidal, not like a perfect circle, is because of soft iron effects. And then those can basically just be removed by calculating the bias and normalizing the values, and then that gets rid of all the problems. So this is what the data looks like after the hard iron and soft iron removal. You can see it's a perfect circle. So I decided to use Euler angles because there's no risk of getting into the singularity error because you're never going to 90 degrees bank, so quaternions are not really needed. And then you just calculate the pitch and roll after all the filtering by using these equations, and then that gives you attitude and heading values. The GPS uses serial UART, and it sends NMEA messages like this, and this is how the aircraft determines where its position is. So then the INS basically just takes in a whole bunch of information from the previous systems that I mentioned, and also combines it with an altitude estimation from a barometric and temperature sensor, and also an airspeed estimation based on using measurements from a dynamic pressure sensor, which is mounted in the front of the airplane to measure airspeed. And then with this information, it estimates the INS state, which has a whole bunch of parameters that describe the airplane, the motion, and also the orientation. And then it uses guidance calculations based on what waypoints are entered into the airplane in the waypoint manager, and it just uses the INS state to calculate the vector that it needs to reach the next waypoint. So then I used this equation from the BMP datasheet to estimate the altitude above sea level, and then I strapped it to the airplane and flew it around a bit and recorded the results from the GPS and the barometer. And then this was the outcome. So the problem is the GPS altitude is pretty slow, and the barometric altitude is quite fast to react, but it suffers from this offset error, which I correct by just reading the GPS value on the startup of the UAV and then just minusing that, and then getting the real value. So then to measure airspeed, there's a pitot tube mounted in the front of the airplane, and then using these equations you can calculate the velocity based on the dynamic pressure that you read from the sensor. It was pretty accurate. After some calibration, this was the result. And the reason the airspeed is different to the ground speed has to do with the fact that it measures the speed of the air coming to the airplane, not the speed of the airplane moving over ground. The airspeed is more important because it describes the aerodynamics a lot better, and that's the reason why I used it in the centripetal acceleration compensation. And then I use an equirectangular projection to get the Cartesian equivalent of the latitude and longitude. This makes it possible to actually calculate the guidance calculations because latitude and longitude is nonlinear. And then because the magnetometer points to magnetic north and not the geographic north pole, you have to do the compensation in the INS by using the magnetic variation angle from the GPS. So then all this information from the INS system goes on to the main guidance control, which, like I said, is the main function of the microprocessor. It starts with a whole bunch of checks and that sort of thing to make sure that everything's running properly. Obviously, for safety reasons, you don't want to allow the UAV to take off when something's broken, so it does the startup procedure. And then it also has a main FSM loop that does certain things based on what flight mode the UAV is in. So then to tune the PID loops for the stabilisation, I designed a 3D model for X-Plane, the simulator. And you can see the blade element theory components on the wing, and this is a simulator that I designed to tune the system. And then after tuning the system, these are the PID constants that I got. In those PID constants I use in a discrete PID controller algorithm that's programmed on the microprocessor, and then this controls the stabilisation of the aircraft. And then for the fire detection, I decided to use a feed-forward neural network with a square error backpropagation with a sigmoid function arctangent. And it takes three inputs, the carbon monoxide sensor, the smoke sensor, and the temperature, and then it produces two outputs based on whether or not there's a fire or not. And then I developed a MATLAB training script to train the information from first principles. And then using that MATLAB training script, I ran through a whole number of different parameters and determined the best number of hidden neurons. So then I decided to implement a robotic path planning algorithm, a motion planner, to make operation of the UAV more safe for the operator, so that it doesn't crash into mountainous terrain, so there's an element of terrain avoidance, and also to make the path as efficient as possible based on energy loss and distance traveled. So the motion planner takes user inputted waypoints and then equirectangularly projects them into the Cartesian plane. And then it constructs a terrain mesh between those points using NASA SRTM topology information. And then with that mesh, it adds a safety height to avoid trees and that sort of thing. And then it applies an A-star optimal path algorithm on that to determine the best path, and then projects it back into geographic coordinates and gives it back to the user interface to be loaded onto the UAV. So I also designed a custom heuristic for the A-star search based on distance as well as climb, since most of the energy wasted is during a climb because of the throttle being increased and also the amount of drag that comes over the airplane. And then I just use a factor that penalizes climb called KZ. For the first test of the autonomous navigation, all the components were mounted on the UAV, and it was programmed with 3 waypoints on the ground control station, after which it was taken off and engaged in autopilot, where it navigated the 3 waypoints. So it's important to note as well that all these 3 waypoints were less than 150 meters from one another, which is way tighter than a usual application for this UAV would be, so these turns were quite tight. So the telemetry information for that flight was recorded on the ground control station and subsequently plotted. This one shows the distance to the current waypoint versus time. And you can see the distance to the next current waypoint reaches a minimum, and then the waypoint is reached. That threshold was set at 15 meters, but the average waypoint intercept distance was calculated as just over 8 meters, so that was better than the spec desired. Now, this is the plot for the latitude and longitude of the UAV over time. You can see the auto navigation is enabled in the bottom red dot, and then the flight path goes along to reach the first waypoint around sample 50, and then it moves on to the second waypoint where it does a few circles around it, but this is due to the fact that the course PID was not set strong enough, and the wind conditions for this particular day were around 14 kilometers an hour, whereas the spec maximum wind condition was 12. So the UAV ended up being blown slightly off course, where it was corrected and reversed, and then returned back to fly and reach the third waypoint, which you can see around the top left of the diagram. So qualification test 2 was basically to test the flight stabilization, and the spec was at least 5 Hz for an update rate, but by using interrupts and a scheduler for the INS, the update rate could be increased to 30.86 Hz, which was tested with an oscilloscope connected to a pin, which was toggled every time the flight control surfaces were updated. So the flight stabilization was tested in a windy condition within spec, and the results are plotted here. The noise seen on all axes is basically the effect of wind disturbances on the aircraft. But in general, the flight stabilization worked well after the settling time. If you look at the pitch angle, it stays within 5 degrees after settling time. The roll angle experiences a disturbance at the 50-second mark, which is assumed to be a lateral wind, but shortly after that it comes back and it stays well within the 5-degree limit. The yaw angle may look like it deviates, but this is only by a single degree. So qualification test 3 was basically just to test the power consumption, which is expected being at least 30 minutes. The battery consumption was measured at several throttle settings with the BEng battery analyzer, and it was found that if the UAV flew with 50% throttle or less for at least 78% of the flight time, it would achieve over 30 minutes flight time effectively. So for qualification test 4, the fire detection neural network was trained. First, a small fire contained by a metal container with an open top is ignited, and the sensor sampling microcontroller is held above the chimney from which the smoke is emitted. A total of 1,000 samples were recorded, half of which in open air and the other half above the smoke. And as was determined previously, the optimum number of hidden neurons was 3. So the network was trained with a 600 sample training set, 150 sample validation set, and 150 sample test set, with the learning rate alpha set as 0.02. So the training characteristics for the fire detection AI using square error backpropagation feed-forward neural network is shown here. The detection accuracy corresponds to about 99%. The main objective of this qualification test was to determine the effectiveness of the motion planning algorithm's implemented energy-saving heuristic. An example scenario was created where a hypothetical UAV operator would place a waypoint beyond the ridge. If effective, the UAV path planner would find the shortest path to reach the goal waypoint. In addition to this, the KZ climb penalty factor was varied to show the different approaches the motion planner artificial intelligence would take based on how much energy it is allowed to lose in climbing. The resultant plots are shown. Increasing the climb penalty factor KZ from 0 to 20 increased the total path distance by about 62%, but decreased the loss in energy from climb by 76.2%. So the first path shows a path plan that simply takes the UAV straight over the ridge for the shortest path. The total change in altitude is 156 meters. The second path plot shows a path plot where the artificial intelligence has decided to circumnavigate the mountain ridge in favor of a flatter flight path with less change in altitude by navigating through the gorge. The path planner prevents the UAV from colliding with the terrain by implementing a minimum above ground height that is apparent in the plots. So it's apparent that the motion plan algorithms that were implemented and proposed work the way they were designed to. The implemented ground control station path planning solution will thus be a valuable tool in increasing the usability and safety of the UAV operations in mountainous areas, as well as in situations where the UAV operator has no true idea of the area where the UAV needs to operate.